This is the modified Atwood's machine, and in this situation we have a car which weighs 1.5 kilograms, no friction on the car, attached to a string. The string goes over a pulley and is connected to a mass of M2, which is 0.5 kilograms. First thing we want to do is draw a force diagram for the cart and the mass. So this is going to be the cart. We're going to have force of the earth pulling down on the cart, which is equal to the mass of the cart times the gravitational field strength of the earth, which is 10 newtons per kilogram, or 10 newtons per kilogram. So this will be 15 newtons. We also have the normal force pushing up, equal amount to the earth pulling it down. That's just going to be N. And we know these are equal because our acceleration is 0 in the vertical direction, so our forces must be balanced. We also have T, which is the tension of the string pulling an unknown amount at the moment. For the weight, we are going to use another teal dot, and we have the force of the earth pulling this boy down. That's going to be the weight of this. The weight of our little block, which is M2, times the gravitational field strength of the earth, which is 10 newtons per kilogram. So we're going to get 5 newtons. And then we have T providing a lesser force than the M2G up. These two T's should be equal. I'm just drawing them unequal for dramatic effect. So now we got our force diagrams pinned down. We're going to calculate the acceleration of the system. To do this, we use our formula. Acceleration equals F net over mass. We know the mass of the whole system is 1.5 plus 0.5 kilograms. So that's just going to be a nice 2 kilograms. To get our net force, we're going to use our net force is the unbalanced force. The two tensions cancel each other out, and the M1G and the normal force cancels each other out. So our net force is just going to be M2G. Let me write that out for clarity. So our acceleration is just going to be 5 newtons over 2 kilograms. So our acceleration will equal 2.5 meters per second, or per second squared. So that's great. Now we want to calculate the tension in the string. In order to do this, we're going to use our acceleration number, or the acceleration of the system, and we know that the acceleration of all the parts of the system, the cart and the weight, have to be equal to the acceleration of the whole system. So we're going to use the equation of the acceleration of one of the parts, but use the number from the acceleration of the whole system in order to find the tension. So we're going to use the equation of the acceleration of our weight. So acceleration of the weight is going to equal, let me do this in a different color for clarity. The acceleration of that weight will be equal to the net force on that weight over the mass of that weight, which we know is 0.5 kilograms. So we are going to figure out the net force. Our net force, using the force diagram, is just going to be the M2G minus our T. So our acceleration will equal the net force, which we just figured out, is M2G minus T. All over our mass of the whole thing, or our mass of just the weight, which is 0.5 kilograms. So we know M2G is 5 newtons, so we can plug that number in. We can go acceleration equals 5 newtons minus t all over 0.5 kilograms. And we know the acceleration of the system is 2.5, so we can substitute that in. 2.5 is equal to 5 newtons minus tension over 0.5 kilograms. So we're going to work this out. We're going to do 0.5 kilograms times 2.5 meters per second, which will give us 1.25. And that's going to equal our 5 minus t. We're going to work this guy out, and we're going to figure out that t is going to be equal to 3.75 newtons. So right there, we got our tension of the string, and right here, we got our acceleration of the system.